Imagine for a second that you were standing perfectly still.
Okay.
You're in your room, maybe you're on your commute, just standing or sitting there. You feel stable, right? The floor feels solid under your feet.
Completely solid.
The road feels hard. It feels, well, permanent. But here is a mind-bending fact to kick things off. The ground beneath your feet is moving. It is not stable at all. We are, all of us right now, riding on these massive plates that are constantly shifting, constantly crashing into one another and pulling apart.
It's a bit unsettling when you really stop and think about it. We treat the ground as the one constant variable in our lives, but geologically speaking, it's actually, well, it's a fluid variable. It's restless.
Restless, I like that. Exactly. And if that isn't enough to shake your worldview, picture Mount Everest. We all know it. It's the highest peak in the world, the ultimate challenge for climbers, the roof of the world.
Pinnacle.
But, and this is the kicker, if you were to drain the Pacific Ocean, just, I don't know, pull the plug and let all the water run out, you would find a mountain called Mauna Kea in Hawaii.
And if you measure Mauna Kea from its base, at the very bottom of the ocean floor, all the way to its peak, it is actually taller than Everest.
It really changes your perspective on what high and deep even mean. You realize that the ocean hides landforms just as dramatic, if not more so, than the ones we see on the surface.
We're completely biased by what we can see above the waterline.
Totally. We have a very surface-level view of our own planet.
Absolutely. And that is exactly what we are going to be doing today. We are going to be looking below the surface. Welcome, everyone, to a special deep dive session.
And we should be specific.
Yes, for everyone tuning in, this is a full summary for UPSC, and it's brought to you by the Simplified UPSC by PPP YouTube channel.
That's right. And our mission today is pretty straightforward, but it's crucial. We are going to decode the NCERT Class 6 Geography Chapter 6, Major Landforms of the Earth.
Now, I can already hear what some of you are thinking. Class 6? Seriously? I'm preparing for the civil services. I'm studying for the toughest exam in India. Why on earth are we going back to 6th grade? It's a fair question. It really is. But it's a dangerous assumption to think you can just skip this material.
Why is that?
Because we aren't just reading a 6th grade textbook here. What we're doing is treating this as the foundational bedrock. If you want to answer those high-level civil services mains and prelims questions, and we are going to look at several of them today, you simply have to understand these basics. This is where it all starts.
So basically, you can't write a complex essay on, say, plate tectonics if you don't fundamentally understand what a mountain actually is.
Precisely. You cannot write a nuanced answer about tectonic stability or resource distribution in a mains paper if you don't grasp the fundamental difference between a fold mountain and a block mountain. It's that simple. You can't run if you can't walk.
Okay, so before we start moving tectonic plates around, I just have a very humble request for you, our listener. If you are finding value in this deep dive, please, it would mean the world if you could subscribe to the Simplified UPSC by PTP YouTube channel.
It genuinely helps the algorithm find other serious aspirants just like you.
It really does. And if you are capable and you want to keep this super useful content coming, your support on Patreon is, well, it's massive for us.
It really is. And on that note, a huge, heartfelt shout out to all of our current supporters.
Yeah.
You are the ones who help us create this content. You are the fuel for this engine. We couldn't do it without you.
Also, please engage with us, like the video or the audio if you're listening that way, and share your comments. We genuinely want to know what you think.
And for the serious aspirants out there, listen up, because this is important. We have free notes with practice previous year questions or PYQs available right now on our public Telegram channel.
And for those who want the complete package, we're talking access to all the videos of this series at once, plus organized premium notes.
And those notes include detailed breakdowns, extra PYQs, and even model mains answers.
Then you should join the private Telegram library. Just send a DM on the public Telegram channel to get access.
Okay, business out of the way.
Let's get our hands dirty. We said the ground is moving. Let's unpack that. The source material talks about two great processes. It frames it like a never-ending tug of war happening on our planet.
That is a great analogy, actually, because landforms aren't static sculptures. They are dynamic. They're always changing. And they are the result of this constant battle between what we call the internal process and the external process.
Okay, let's start with the internal process. This is the stuff happening deep down, right? The engine room of the Earth.
Correct. This is movement occurring within the Earth. We often forget that the Earth is incredibly hot inside. It's molten, it's fluid, It's, as we said, restless.
And all that energy has to go somewhere.
Exactly. This internal energy generates immense forces that push the surface up in some places and pull it down in others. The technical terms in the text are upliftment and sinking.
So when I see a mountain, a huge range like the Himalayas, that's usually the earth pushing up. That's upliftment on a massive scale.
Generally, yes. Upliftment gives us those elevations, the mountains, the plateaus. But sinking is just as important. Sinking creates depressions, basins, and these vast rift valleys. It's the earth literally reshaping itself from the inside out.
I like the analogy in the source. It's like a pot of boiling soup.
It is. The heat from below causes the surface to bubble and churn and change shape. That's a perfect visual for the internal process.
Okay, so that's one side of the tug-of-war. What's the opponent, the external process?
Which is happening right here on the surface where we live. This is the world of wind, water, and ice.
So if the internal process builds things up, does the external process tear them down?
That's precisely it. The external process is the continuous wearing down and rebuilding of the land surface. It's driven by the atmosphere and the hydrosphere. These forces are the great levelers of the planet. They see a mountain and they want to make it flat.
And there are two key terms here that we absolutely need to nail down because I see students mixing these up all the time. Erosion and deposition.
Ah, yes. The classic pair. They are two sides of the very same coin. Let's start with erosion.
Okay.
Erosion is the wearing away of the Earth's surface. Its primary function is to lower the surface. Imagine a river carving out a valley over millions of years, or wind stripping away topsoil from a field. That is erosion. It's destructive, in a sense. It scrapes the earth away.
And all that material that gets scraped away has to go somewhere. That's where deposition comes in.
Exactly. Matter cannot be created or destroyed, right? It just moves from one place to another. So all that eroded material, the sand, the silt, the stones, has to be dropped somewhere. When the agents of erosion, like a river flowing out into the sea or wind slowing down, lose their energy, they drop that load.
And that's deposition.
That is deposition. It deposits the material and it raises the surface elsewhere. It's the constructive part of the external process.
So to put it simply, internal processes push the land up and external processes try to grind it back down.
Precisely. It's a constant dynamic cycle. And if we want to connect this to the bigger picture, as we always should for our aspirants, this is essentially the interaction between the lithosphere, the land, the atmosphere, the air, and the hydrosphere, the water.
And the biosphere, that's us, plants, animals, we exist right at the intersection of all these massive forces.
We live in the battleground of this tug of war.
It's interesting you mentioned the bigger picture because this connects directly to a UPSC mains question from 2016. It was question 16, and it asked about the changes in the shape and size of continents and ocean basins due to tectonic activities.
That is a perfect linkage, an absolutely perfect one. When the NCERT Class 6 text mentions internal processes, it is simplifying the grand concept of plate tectonics. The movement of crustal masses, the drifting of continents, that is the internal process on a global scale.
So as an aspirant, when I read upliftment and sinking in this Class 6 book, I shouldn't just think, oh, a hill goes up.
No, absolutely not. You should be thinking plate tectonics and continental drift for your mains preparation. You need to be able to draw a direct line from this simple textbook definition all the way to the complex, multifaceted answer that's required for the exam.
Okay, that's a key takeaway. Let's move on to the actual result of these processes. The source categorizes landforms based on their elevation and their slope. And the first major landform is the most dramatic one, mountains.
The definition they give is simple, but it's very specific. A mountain is any natural elevation of the Earth's surface. It typically has a small summit and a broad base. And crucially, it is considerably higher than the surrounding area.
Small summit, broad base. That's a crucial visual, isn't it? Because a plateau might have a broad base and it's high, but it doesn't have that small, pointy summit.
Exactly. That distinction in shape is key. And mountains, well, they have a very distinct relationship with the atmosphere. There's what we call a climate gradient.
Meaning as you go higher, the climate changes.
Drastically. As you go up, the temperature drops. The air gets thinner. The climate becomes harsher. It's the reason you can have a hot, tropical jungle at the base of a mountain in the Andes and a frozen, barren wasteland at the top.
That's why we see those permanent snow caps, even in tropical regions, if the mountain is high enough, like Mount Kilimanjaro in Africa.
Right. And in some mountains, it gets so cold that entire rivers of ice are formed. These are called glaciers. They are permanently frozen rivers, and they are moving. Very, very slowly, but they are moving.
And they're powerful, right? They carve out the landscape.
Incredibly powerful. They are some of the most powerful agents of erosion on the planet. They can gouge out entire valleys.
And because of this harsh climate, you've got the steep slopes, the intense cold, the lack of flatland. Mountains are generally thinly populated.
It's just simple economics of survival, isn't it? You can't easily practice large-scale agriculture on a 60-degree slope. You can't easily build a house or a road. So historically, mountains have been barriers to movement, or they've been refuges for people, but they've rarely been population hubs.
Now, you mentioned Mauna Kea in the intro, and I want to circle back to that because it's such a great aha moment. Not all mountains are visible to us standing on land.
Yes, this is a favorite fact for geography nerds, and for good reason. Mauna Kea in Hawaii, if you measure it from its true base, which is on the floor of the Pacific Ocean, it is 10,205 meters high.
Wait, let's put that in context again. Mount Everest is what?
8,848 meters above sea level. So structurally, from base to peak, Mauna Kea is significantly taller. It just happens that most of its bulk is underwater.
It really reminds us that our sea level reference point is, well, it's arbitrary when you're measuring the actual size of a landform.
It is. We measure success by what we can see, but nature builds regardless of where the waterline happens to be.
Speaking of depth, the source also mentions the deepest point on Earth, the Mariana Trench.
Ah, yes, the other extreme. It's 11,022 meters deep in the Pacific Ocean. That depth is actually greater than the height of Everest is above sea level.
Wow. So if you could somehow pick up Mount Everest and drop it into the Mariana Trench.
The peak would still be underwater by over 2 kilometers. It just gives you a sense of the sheer vertical scale of our planet's crust. It's massive, both up and down.
That is just mind-boggling. Okay, back to the mountains we can see. They aren't usually just random, isolated bumps on the landscape, are they? They seem to have a kind of social life.
They are very social creatures, yes.
Really?
They like to hang out in groups. Mountains are very often arranged in a long line, and this line is known as a range.
And these ranges can be huge.
Oh, massive. They can extend for hundreds, even thousands of kilometers.
Like the Himalayas in Asia, that's a classic example.
The perfect example. Or you have the Alps in Europe and the Andes in South America.
The Andes is a good one to remember for prelims, isn't it? Because of its length.
Yes, the Andes is actually the longest continental mountain range in the world. It runs down the entire western spine of South America. It's like the backbone of that continent. It dictates weather patterns, drainage, everything.
Now, here's where it gets really interesting for our listeners, especially those preparing for exams. Not all mountains are born the same way. The source classifies them into 3 main types. And we need to break these down because the mechanism of formation is so key for Maine's answers.
Absolutely.
First up, fold mountains.
This is the most common type we see, the big ones. The source uses a great little experiment to help you visualize this. For anyone listening, just imagine you have a pile of paper on your table.
Okay, I've got my imaginary stat of paper.
Now, put your hands on the opposite edges of the pile and slowly push them towards each other. What happens?
The paper buckles. It has to. The center rises up into a peak because it has nowhere else to go. It gets squeezed upwards.
Exactly. That is a fold mountain. It's formed by the collision of 2 tectonic plates. The crust gets squeezed, the technical term is compressed, and it folds upwards. It literally crumples like the hood of a car in a head-on crash, just happening over millions and millions of years.
And within this category of fold mountains, the source makes another distinction. It talks about young fold mountains and old fold mountains. What's the difference? Is it just a number, an age?
It's about age, yes, but that age dictates their physical appearance, their character. The Himalayas and the Alps are classic examples of young fold mountains.
Young in geological terms, meaning what? A few million years old?
Meaning tens of millions of years old rather than hundreds of millions. And because they're relatively young, erosion hasn't had enough time to grind them down yet. So what do you see? You see rugged relief and high conical peaks. They are sharp, they are jagged, they look angry and energetic.
And the old ones. The source mentions the Aravalli Range in India.
A perfect example. It's one of the oldest fold mountain systems in the entire world.
I've seen the Aravallis. They look nothing like the Himalayas. They're much, much lower. They're rounded. In some places, they're almost just like rolling hills.
Exactly. And that's key. At one point in deep geological history, the Aravallis might have stood as tall and proud as the Himalayas do today. But because they are so incredibly old, the external processes, the wind, the rain, the heat, the ice, have been attacking them for eons. They have been worn down. They now have low elevation and rounded, gentle features.
So this is a real-life example of that tug of war. The internal process built the air valleys up, and the external process has slowly but surely won the battle and ground them down.
It's the ultimate proof that, given enough time, erosion can conquer even the tallest mountains.
The source also gives a couple of other examples of these old, worn-down fold mountains, the Appalachians in North America and the Ural Mountains in Russia.
Correct. The Urals are particularly significant because they form the traditional physical boundary between Europe and Asia. They are the seam between those two continental landmasses.
Now, let's bring in a heavy-hitter question. This is where we really earn our keep for the aspirants listening. It's from UPSC Mains 2014, question 17. And it's a two-parter. It asks, why are the world's fold mountain systems located along the margins of continents? Bring out the association between the global distribution of fold mountains and the earthquakes and volcanoes.
Oh, that is a classic, a fantastic question, because it forces you to synthesize multiple concepts. It's a perfect example of how a simple concept like fold mountain explodes into a complex, interconnected answer.
So let's break it down. First part, why the margins? Why at the edges of continents?
Well, let's go back to your pile of paper. Where did you have to push from to make it fold?
From the edges, from the margins.
Exactly. Fold mountains are at the margins because that is where the tectonic plates collide. The margins of the continents are very often the boundaries of these plates. The Himalayas are being formed at the margin where the Indian plate is crashing into the Eurasian plate. The Andes are at the margin where the South American plate is colliding with the Nazca plate. That's the crash zone.
Okay, so that answers the where. What about the second part, the association with earthquakes and volcanoes? Why do they all hang out together?
Think about the sheer violence of that collision. When two massive plates of rock, thousands of kilometers wide, are crashing into each other, you don't just get gentle folding. You get immense friction. You get stress building up in the rock until it snaps.
And that snap is an earthquake.
That is your earthquake. And it's even more than that. Often, one plate, usually the denser oceanic plate, dives under the other. This process is called subduction. Now, when that plate goes deep down into the hot mantle, what happens to it?
It melts.
It melts. And that molten rock, now called magma, is less dense than the surrounding rock, so it wants to rise. It forces its way up through cracks in the crust and erupts on the surface. And that's how you create volcanoes.
So fold mountains, earthquakes, and volcanoes are essentially a geological trinity, a package deal.
Yes, they are a trinity found at convergent plate boundaries. You almost always find them together. The Ring of Fire around the Pacific Ocean is the perfect example of this. It's a ring of high fold mountains, constant earthquakes, and active volcanoes. It's the most geologically active zone on the entire planet.
That is a fantastic synthesis, and if you can explain that connection clearly and concisely in your mains paper, you've absolutely nailed that question.
You have.
Okay, let's move on to the second type of mountain, block mountains. This sounds a bit more geometric, less about folding and crumpling.
It is. Instead of folding, I want you to imagine the Earth cracking under stress. Block mountains are created when large areas of the crust are broken and displaced vertically. This usually happens due to tension forces pulling the Earth apart, rather than the compression that causes fold mountains.
So not squashed, but pulled or sheared apart.
Right. Think of a big block of cheese. If you slice it down the middle, and then you push one slice up and let the other slice drop down, you create these jagged vertical edges. That's a block mountain system.
And we have some very specific terminology here that sounds, I think, quite German. Horsts and Graben.
Yes. The block of land that gets pushed up is called the Horst, and the block that drops down is called the Graben.
I always remember it because Graben sounds a bit like grave, so it's the one that goes down into the ground.
That's the good mnemonic. It works. The source gives the Rhine Valley and the Vosges Mountain in Europe as classic examples.
So in that landscape, the Vosges mountain range is the Horst, it's the uplifted block, and the famous Rhine River flows through the Graben, the lowered block.
Exactly. The Rhine is flowing through what's called a rift valley, a valley created by the sinking of the Earth's crust. The river didn't carve that entire valley from scratch. The Earth dropped, and the river simply took the easy path of least resistance.
Okay, that makes sense. So number 3, volcanic mountains.
These are probably the most straightforward to visualize. They are built simply by the accumulation of volcanic material.
This is the classic volcano shape we all drew as kids in school, the cone.
Yes. Magma from within the Earth builds up, erupts at the surface as lava, ash, and what the text calls lava bombs, and all of this material piles up layer after layer to form a cone shape. It's construction by eruption.
And the famous examples.
The book mentions Mount Kilimanjaro in Africa and the beautiful Mount Fujiyama in Japan. Fujiyama is an almost perfectly symmetrical cone. It's stunning.
I love the description in the source lava bombs. It sounds so destructive and violent.
It is destructive in the moment, absolutely.
Right.
But it's fascinating how these destructive forces create features that are, in the long run, incredibly useful to us. We shouldn't just see mountains as geological accidents or hazards.
No, they are absolutely vital. Let's move into that. Segment 4, the utility of mountains. The source calls them a storehouse of water. That's a great phrase.
It's a beautiful phrase, and it's perfectly accurate. Because of the glaciers, many of the world's most important rivers originate from glaciers high up in the mountains. In India, the Gangotri Glacier feeds the Ganga. The Yamunotri Glacier feeds the Yamuna. These rivers are the lifelines of the entire northern Indian plain.
And this connects directly to a prelims question from 2019. It was one of those tricky matching questions. It asked aspirants to match glaciers to the rivers they feed.
Yes, that was a tough one because it required very specific knowledge, not just a general understanding. Let's run through it. You had Bandarpunch, which matches with the Yamuna,
Okay.
Barshigri with the Chenab, Milam with the Mandakini, Siachen, the famous one, with the Nubra River, and Zimu with the Menas.
Wow. If you didn't know that mountains are the water towers of the world, you might not realize just how critical these specific glacier-river connections are for regional hydrology.
Exactly. And for any aspirant listening, I'd say go look at a map right now.
Yeah.
After this, find Bandarpunch on a map. Locate Zimu. Visualizing where the water comes from helps you understand the entire river system downstream, the politics of water sharing, the planning of infrastructure. It often starts right there at the glaciers.
And it's not just about drinking water, is it? We use that mountain water for hydroelectricity and for irrigation.
Yes, mountains act as natural dams in a way. They provide the steep gradient, the height, needed for hydropower. Falling water has a huge amount of potential energy, and mountains provide the height for that fall.
What about agriculture? This seems counterintuitive. We said mountains have steep slopes, which seems bad for farming.
It is, in its natural state.
Yeah.
But humans are ingenious. The source explicitly mentions terraces. You literally cut steps into the slope of the mountain.
There's a giant staircase.
Exactly. This does two crucial things. One, it creates flat areas where you can plant crops. And two, and this is the most important part, it stops the water from just rushing down the slope and washing all the precious soil away. It captures the water and the nutrients at each level.
Which brings us to another fascinating PYQ. This is Maine's 2014 question 21. Whereas the British planters had developed tea gardens all along the Shivaliks and Lesser Himalayas from Assam to Himachal Pradesh, in effect they did not succeed beyond the Darjeeling area. Explain.
This is a brilliant, brilliant question because it tests if you understand the nuance of mountain climates and soils. It's not enough to know mountains have slopes. You have to know more.
So you have two mountainous regions. Both have slopes. Both get rainfall. But the question asks why tea cultivation was a huge success in one place, but not so much in the other.
And the answer comes down to a very specific combination of factors. Tea is a fussy plant. It needs well-drained slopes. It absolutely hates having its roots sitting in standing water. But at the same time, it needs very high humidity and evenly distributed rainfall throughout the year.
And Darjeeling offered that perfect combination.
It did. The soil conditions, the mists, the specific rainfall patterns were perfect. The Shivaliks further west, in places like Himachal, they have a harsher, colder winter, a different rainfall pattern, which is more concentrated in the monsoon season, and soil that just wasn't as hospitable for the specific tea varieties the British were trying to plant at a commercial scale.
So it's not just mountains are good for tea, it's specific mountain conditions are good for tea.
Exactly. Geography is all about the details. You can't just paint with a broad brush.
And speaking of slopes and farming, the source also touches on the problem of soil erosion,
which was part of a prelims question in 2013. It linked soil erosion to terrace cultivation, or rather the lack of it, and deforestation in tropical climates. In mountains, the soil layer is often very, very thin. If you don't have forests with their roots to hold the soil in place, or terraces to slow the water down, that fertile top layer just washes away instantly when it rains. It's like trying to wash soap off a tilted plate. It's gone in a second.
Right. And of course, mountains are also biodiversity hotspots and huge tourist magnets. The source lists sports like paragliding, hang gliding, river rafting, skiing.
They are idyllic sites, as the text says. But that tourism, as important as it is for local economies, brings its own immense environmental pressure, which is something every future civil servant absolutely needs to consider. The idea of sustainable tourism is a huge topic for India. How do you bring tourists to the Himalayas without destroying the very pristine beauty they came to see.
A huge challenge. Okay, let's come down a little bit in elevation. We are leaving the pointy peaks and we're landing on the table. Segment 5. Plateaus.
A plateau is an elevated flatland. The text calls it a tableland, which is a perfect description. It stands high above the surrounding area, so it usually has steep sides, but it has a relatively flat top, unlike the conical peak of a mountain.
And the heights of these plateaus can vary hugely, right?
Oh, massively, from just a few hundred meters above sea level to the incredible Tibet Plateau. The Tibet Plateau is the highest in the world. It averages between 4,000 to 6,000 meters above mean sea level.
Wait, that's higher than many mountains in the Alps.
It is. You could be at 5,000 meters, an altitude that would be a major peak elsewhere, and you can still be on relatively flat ground. That's the Tibet Plateau. It's rightly called the roof of the world.
We have some other key examples to remember for the exam as well.
Yes. The Deccan Plateau in India, one of the oldest and largest plateaus. The East African Plateau, which covers parts of Kenya, Tanzania, and Uganda. And the Western Plateau of Australia.
Now, we established that mountains give us water. So what do plateaus give us? Why should a civilization care about these high, flat, often dry and rocky places?
One word: minerals. That's the key word for plateaus. They were the mining heartlands of the world.
Why is that?
The geology of plateaus, especially old ones, often exposes ancient mineral-rich rocks at or near the surface. The African Plateau, for example, is world famous for its gold and diamond mining.
And what about in India?
The Tectonic Plateau.
Yeah.
It is the mineral heartland of India. It has huge reserves of iron, coal, and manganese. It's what fueled India's industrial development.
This links perfectly to another mains question. Mains 2014, question 23. Account for the change in the spatial pattern of the iron and steel industry in the world.
This is where you have to connect physical geography to economic geography. Let's think about it. Initially, where would you locate an iron and steel industry? Close to the raw materials, the coal and the iron ore.
Because they're incredibly heavy and expensive to transport.
Exactly. You don't want to transport them far. It's too expensive. And where do you find them in abundance? On plateaus. So the early industrial hubs of the world, like Pittsburgh in the U.S., the Ruhr in Germany, or Jamshedpur in India, were tied directly to these geological features.
So knowing the location of the world's major plateaus literally tells you where the old industrial cities are located.
In many cases, yes. It explains the economic history of the 19th and early 20th centuries. The industry has shifted since then, due to new technologies and access to coastal ports for imports, but its historical roots are firmly in the mineral-rich plateaus.
Plateaus also give us waterfalls, which makes sense. The rivers are flowing on the flat top and then they just drop off the steep edge of the table.
Correct. The source mentions Hundra Falls on the Subarnarekha River in the Chotanagpur Plateau and the famous Jog Falls in Karnataka. And these are, of course, prime locations for generating hydroelectric power because you have that sudden massive drop in elevation.
And surprisingly, agriculture. I always pictured plateaus as being rocky and barren.
Many parts are, but not all of them. We have a special type called a lava plateau. The Deccan Plateau in India is a prime example of a lava plateau.
Meaning it was formed by volcanic lava that spread out over a vast area.
Yes, millions and millions of years ago, through what we call fissure eruptions. Not from a single volcano cone, but from long cracks in the earth. The lava was very fluid. It spread out like water over thousands of square kilometers, cooled, and formed thick layers of a rock called basalt.
And what happens to that basalt rock over time?
When that basalt lava weathers down over millions of years, it breaks down and forms a very specific type of soil, black soil.
Also known as rigor soil, or cotton soil.
Exactly. It's a very fertile, moisture-retentive black soil. So far from being barren rocks, some plateaus are actually agricultural gold mines for specific crops like cotton. This is why the regions of Maharashtra and Gujarat on the Deccan Plateau are the historic heartland of India's cotton and textile industry. The geography dictates the economy.
Okay, so let's come all the way down now. From the jagged peaks of the mountains to the flat tables of the plateaus, and now down to the lowlands. Segment 6. Plains.
The flatlands. Generally, these are large stretches of land that are not more than 200 meters above sea level.
So how do we get these vast, flat stretches? Did the Earth just decide to be flat in these places?
Mostly they're the creation of rivers. We talked about erosion in the mountains, right? The rivers act like conveyor belts, carrying all that eroded material, the sand, the silt, the clay down the steep slopes.
Okay.
But when the rivers reach the gentle slope of the valley floor, they slow down. They lose the energy required to carry all that heavy stuff. So what do? They start dropping their load, they deposit it. And layer by layer, flood after flood, over millions of years, that deposition builds up to form vast flat plains.
So the plains are basically the mountains just ground up into fine particles and spread out neatly by the rivers.
That is a poetic, but actually a very accurate way to put it. The great Ganga and Brahmaputra plains in India, the Yangtze plains in China, they are all formed in exactly this way. They're sediment sinks.
And it's no coincidence that these are the most thickly populated regions of the entire world.
Not a coincidence at all. It's a direct consequence.
So why is that? Why do humans flock to plains?
It's the Goldilocks zone for human civilization. Think about it. The flat land is easy to build houses on. It's easy to build roads, railways, airports. You don't need to blast tunnels through mountains or build expensive bridges over deep gorges every mile.
And the food.
And most importantly, the food. The soil, all that fine silt brought down from the mountains, is incredibly, incredibly fertile. What we call alluvial soil. It provides immense food security.
This was the core of that Maine's 2016 question 17, which asked about the distribution and density of population in the Ganga River Basin.
And the answer is right here in this Class 6 chapter. It's the combination of three things: fertile alluvial soil for agriculture, an abundance of fresh water from the river, and the flat terrain, which is perfect for building infrastructure. That combination makes the Indo-Gangetic Plains a massive population magnet. You simply cannot support that kind of population density in the steep Himalayas or on the dry parts of the Deccan Plateau. The geography dictates the demography.
So we've covered the heights of the mountains, the tablelands of the plateaus, and the flat, fertile expanse of the plains. This brings us to a really crucial segment, the interaction between these landforms and people.
The source makes a very poignant comparison here. It says that life is difficult in mountain areas. The environment is constantly fighting you. Whereas in the plains, life is generally easier, crops grow better, you can move around more easily.
But with that ease comes a certain complacency, perhaps. The source uses the phrase, the wasteful manner of use.
Yes. It specifically highlights the problem of constructing houses and factories on fertile agricultural land. In our rush to urbanize, we are literally paving over the very soil that feeds us. It's an incredibly short-sighted strategy.
And it also mentions pollution. Throwing garbage on the land or directly into the water, there is a very powerful image in the source of a polluted river choked with waste.
It's a stark reminder. And then on top of our own impact, we have to deal with natural calamities. We have earthquakes, volcanic eruptions, storms, floods.
This connects to the kind of forward-looking question you might see, like a projected Maine's 2025 question 7 regarding tsunamis. Tsunamis are often generated by undersea tectonic activity, those internal processes we talked about, but their most devastating impact is felt on the low-lying coastal plains where millions of people live. Our major cities and settlements are often in the most geologically vulnerable zones.
It's a classic human-environment conflict.
The source also has a box about the Swachh Bharat mission. It quotes the idea that a healthy mind lives in a healthy body, and then extends it, saying that a healthy body needs a clean environment, clean water, clean air, clean surroundings.
It's a powerful ethical point embedded in a geography text. The land isn't just a resource for us to exploit today. The text says, and I think this is so important, it is our duty to leave the earth a better place for future generations. That is the entire concept of sustainable development. Simplifies for a sixth grader, but absolutely essential for a future civil servant. You are not just administrators, you are the guardians of this land.
Now, before we wrap up, we need to bridge this general global geography with the specific Indian geography snippets that were provided from the next chapter, chapter 7. Let's ground all these concepts in India.
A great idea. Because India is a perfect microcosm of all these landforms. We have the mighty Himalayas in the north. The name literally means abode of snow.
And they're divided into 3 parallel ranges, right?
Yes. From north to south, you have the Great Himalaya or Himadri. This is the northernmost range. It's continuous, and it contains the highest peaks like Kanchenjunga. Then you have the Middle Himalaya or Himachal. This is where you find all the popular hill stations like Shimla and Manali. And finally, the Shiwalik, which is the southernmost lower range made of unconsolidated sediments brought down by the rivers.
Then we come south to the Great Peninsula.
It's triangular in shape, it's ancient, and its relief is very uneven. It has the Aravallis on the northwest, very old, worn-down fold mountains, and it has the crucial Vindhyas and Satpuras ranges in the center.
And this is important. The rivers Narmada and Tapi flow through those ranges.
That's a critical fact for prelims. Everyone listening, please note this. Narmada and Tapi are west-flowing rivers. They drain into the Arabian Sea. Almost all the other major peninsula rivers, the Godavari, the Krishna, the Mahanadi, the Kaveri, flow east into the Bay of Bengal.
Why do Narmada and Tapi flow west? Is it just random? It seems to go against the general slope of the peninsula.
No, it's not random at all. It's because they flow in rift valleys. Remember the block mountains and the Graben. They are flowing in the Graben, the sunken block, between the Vindhya and Satpura ranges. That rift, that geological fault, directs them westward. It's a classic case of structural control of a drainage system.
That reminds me of that 2014 prelims question about which rivers flow through Arunachal Pradesh. It listed Barak, Lohit, and Subansiri. You absolutely have to know your river maps.
And that 2019 prelims question that asked to match seas to their bordering countries. Geography requires a strong mental map. You need to be able to visualize the Adriatic Sea or the Caspian Sea, just like you need to visualize the Narmada flowing west through its rift valley.
Okay, we also have the coastal plains, which are flanked by the Western and Eastern Ghats.
Right, and the Ghats themselves are very different. The Western Ghats, or the Sahyadri, are a near continuous wall along the west coast. They are what block the monsoon winds and cause that incredibly heavy rainfall in Mumbai and Kerala. The Eastern Ghats are broken and uneven. They're much lower because the east-flowing rivers have cut through them over millions of years to reach the Bay of Bengal.
And finally, we have the islands, Lakshadweep and the Andaman and Nicobar Islands.
Two very different origins, which is a key point. Lakshadweep are coral islands. This was a direct point in that prelims 2014 question, which asked which areas in India have coral reefs. The options included Andaman and Nicobar, Gulf of Kutch, and Gulf of Mannar. But Lakshadweep is unique because the islands themselves are entirely made of coral, built from the skeletons of tiny marine animals called polyps.
And the Andaman and Nicobar Islands?
They are largely volcanic and tectonic in origin. They are essentially the peaks of a submerged mountain range that rises from the seafloor. They are an extension of the same mountain chain that becomes the Himalayas on the mainland.
It is absolutely amazing how much examinable content is hidden in plain sight in these introductory chapters.
That is the secret of UPSC preparation. The complex questions are all built on these simple, fundamental building blocks. If you skip the basics, the advanced stuff will never stick. You can't understand the complex monsoon mechanism if you don't first understand the basic relief of India, the wall of the Himalayas and the Western Ghats.
So, to recap, we've gone from the internal fires of the Earth to the snowy peaks of the Himalayas, down to the mineral-rich plateaus and the fertile, life-giving plains.
It's a complete interconnected system. Internal forces build it up, external forces wear it down, and we, as humanity, try to build our lives somewhere in the middle of that epic ongoing battle.
Here's a final provocative thought for you to chew on as we close. The source material started by telling us that the ground is slowly moving. We know the Himalayas are still rising because the Indian plate is still crashing into the Eurasian plate. But we also know the Aravallis are old and worn down. So if we could fast forward 10, 20, maybe 50 million years into the future, what would the map of India look like? Will the Himalayas eventually stop growing and be worn down to gentle hills like the Aravallis are today? Will a new mountain range rise from the ocean where Mauna Kea currently sits?
That is the beauty and the terror of geology. The map of the world as we know it is just a snapshot in deep time. It has never looked exactly like this before, and it will never look exactly like this again. We are just temporary passengers on a constantly shifting planet.
That is a lot to think about. This has been a deep dive for Simplified UPSC by PPP. We sincerely hope this helps you visualize your geography preparation and connect the dots.
And don't forget, if you want the notes to revise everything we just discussed, especially those crucial PYQ links and breakdowns, please check the Telegram channels.
Please subscribe to Simplified UPSC by PPP on YouTube. Like this video and leave a comment telling us what topic we should dive into next. And if you can, please consider supporting us on Patreon. It keeps the lights on and allows us to keep this content flowing for everyone.
A huge, sincere thank you again to all our supporters. You truly make this possible.
Head to the public Telegram channel for the free notes, or DM us there to join the private library for the premium content, the model answers, and the full series archive.
Keep learning and stay curious.
We'll see you in the next deep dive.